So now that we've talked about cations and anions that can act as bases and acids, we're going to look at salt solutions. So salt solution can either be acidic, basic, or neutral because it has cations and anions in it, and those are potentially acids or bases. So the pH of the salt solution depends on which cations and anions are in them. So if you have a salt solution where neither the cation nor the anion acts as an acid or base, then you get a pH neutral solution. So this would be where the cation is the counterion of a strong base and the anion is the conjugate base of a strong acid. So we have a couple of examples here. Sodium chloride, calcium nitrate, potassium bromide. So if we look at those individual ions, let's just look at that last one, K plus and Br minus. Well, if I make this into an acid, that's HBr. This is the conjugate acid. This argument with this pointer. The conjugate acid of that. And over here, we're going to look at the conjugate base of that, which, well, the base it would come from would be potassium hydroxide. And this is one of the strong acids. This is a strong base. And so those ionize completely, and we're not going to have bromide picking up a hydrogen and affecting the pH of the solution. That makes sense? If we have something where the cation doesn't act like an acid, but the anion acts like a base, we're going to get a basic solution. So down here we have some examples that look similar to those other ones. Let's look at NaF that has sodium ions and fluoride ions. So sodium might come from sodium hydroxide. Fluoride might come from hydrofluoric acid. This is a weak acid. So it only ionizes partially. So if we have fluoride ions introduced into an aqueous solution, they will combine with some of the hydrogen ions that are present in the water. Or we can think of it this way. Fluoride ions will interact with the water, acting as a base. Because the fluoride ions will not be completely dissociated or completely ionized in aqueous solution. Because this is a weak acid. Weak acids, you look at the composition of the solution, and there's a significant portion of the units that are in the molecular form. So if we stick fluoride in there, it's going to attach itself and create HF. When it does that, it's going to produce hydroxide ions. This is the acid, that's the conjugate base. It acts as a base, and so the solution will be basic. Does that make sense? I got a couple of nods and a lot of just dazed stares. So I'm thinking that's not making sense. So let me try again. Let's look at KNO2. So there's two ions there, K plus and NO2 minus. Everyone okay with that? Because if we're not okay with that, we have some other problems. So this is potentially the conjugate acid of a base, and this is the conjugate base of an acid. Okay? So let's make those into acids and bases. So we can take this one and add a hydrogen to it and get HNO2. Everybody okay with that? Now this one, making the conjugate base of this, we can't subtract a hydrogen ion right? Because it's not that kind of an acid or base. But how could this have come from a base? It could come from potassium hydroxide, right? Are there hydroxide ions present in pure water? Yes, there are. Not very many, but they're there. So if we put potassium into pure water where we have hydrogen ions and hydroxide ions, it could conceivably combine with hydroxide ions to form KOH. But is this relationship, is this an equilibrium? Does this go both ways? No. As I've drawn it here, it's going to go completely to the left. Because this is a strong base. It dissociates completely. You don't have any KOH units floating around. It separates into potassium and hydroxide. So if we stick potassium ions into water, they are not going to combine with hydroxide and form these units, because these units don't exist in aqueous solution. Does that make sense? I'm getting mostly nods. So the reason is that this is a strong base. So this comes from a strong base. It is the conjugate acid, but it doesn't act like an acid. It's going to be pH neutral. If we look at this one, NO2, so we put NO2 minus into some water, and there are hydrogen ions present in the water, and so we can envision this forming an acid. This is the conjugate base. Here's our acid. Then we look at what kind of an acid is it, strong or weak? It's a weak acid, right? Because it's not one of the six. So weak acids, when they ionize, it's in equilibrium. They do not ionize completely. So if I throw some nitrite ion in here, it will combine with hydrogen ions to form this weak acid. If it's combining with hydrogen ions, what does that do to the pH of the solution? It makes it more basic. The pH will go up because this is tying up some of the hydrogen ions. Erase that down there. We can think of it a different way. NO2 minus plus H2O can form HNO2 plus hydroxide ions. So it can actually take the hydrogen ion from a water molecule, and now we see there's hydroxide ions that are being produced. Do you see it? Oh, we got more nods. So we're looking at the cation and the anion of the salt, and we're trying to figure out, did they come from a strong acid and a strong base, from a weak acid, from a weak base? Where could they have come from? And that tells us what they might do. So we also have salts where the cation acts like an acid, the anion does not. So then we're going to have acidic solutions. So there's a couple here worth noting. Let's look at NH4Br. So that has ammonium ion and bromide ion. What base does NH4 plus come from? NH3, right? And what acid does Br minus come from? HBr. Are either of these a strong acid or base? Yeah, this is a strong acid, and so the Br minus is not going to do anything to the solution pH. We say that one's pH neutral. But what about ammonia? That's a weak base, right? So there's going to be an equilibrium between these. They will both be present. So if this is the weak base, then this is the conjugate acid. NH4 plus acts as an acid. So I'm putting an acid into the solution. The solution is going to be acidic. Okay with that? These two are going to be more problematic because, like, what the heck? Let's look at FeCl3. So the ions present there are Fe3 plus and Cl minus. And Cl minus would come from HCl, which is a strong acid, so that's not going to do anything. And Fe3 plus, like the iron hydroxide isn't soluble. That's one of the two small, highly charged cations that you have to remember. Yeah. So the Fe3 plus acts as an acid, right? So we're going to get an acidic solution. And, you know, the book gives you the formulas and how it makes the complex ion and stuff. And we'll understand that more when we talk about complex ions. For now, just remember Al3 plus and Fe3 plus act like acids. And then we have the really complicated ones. We've got the cation acting as an acid, the anion acting as a base. And so now the pH is going to depend on the relative strengths of the acid and the base. So if we look at something like here we have not ammonium nitrate, but ammonium nitrite. This one. NH4 plus is the conjugate acid of a weak base. So this is going to make the solution acidic, right? The NH4 plus is going to make it acidic. But when we look at the NO2 minus, that's the conjugate base of a weak acid, and so that's going to make the solution basic. So we have opposing things. The stronger one is going to win. So you compare the Ka of the acid to the Kb of the base. And the higher K value dominates. So this summarizes what we were just talking about. Different combinations of conjugate acids, conjugate bases. So for the cations, we can think of them as counter ions of strong bases. We've also got the small, highly charged metal ions in there, the iron 3 plus and the Al3 plus. And we've got the conjugate acids of weak bases. Okay, let's practice. Determine if the solution formed by each salt is acidic, basic, or neutral. So here we've got sodium hydrogen carbonate. There's two ions. Sodium and hydrogen carbonate. So is sodium the companion to a strong base, a counter ion for a strong base? It is. Sodium plus hydroxide gives sodium hydroxide, but it's not going to form that. The sodium hydroxide ionizes or dissociates to form sodium and hydroxide ions. So is that going to contribute to the change in pH? No. So that's going to be neutral. HCO3 minus is at the conjugate base of a weak acid. Yeah, it is. If we add a hydrogen to this, we get carbonic acid, H2CO3. It's a weak acid because it's not one of the 6 strong acids. So this is a weak acid. This is the conjugate base. It acts as a base, and this solution is going to be basic. Does that make sense? Any questions? So let's look at this one. CH3, CH2, NH3Cl. That probably looks pretty strange to you. Well, break it into 2 ions. What's an ion that you recognize in there? Cl, chloride, right? So we'll have chloride and we'll have the rest of it, right? So the rest of it is CH3, CH2, NH3, and we've got chloride with a -1 charge. What's the charge on the cation? +1. So we're more comfortable with chloride. Let's look at chloride first. So chloride is the conjugate base of an acid, but what kind of an acid? A strong acid. So this is pH neutral. It's not going to contribute to any pH change. Now this weird looking guy. Is there a part of this that looks a little familiar? The very end here, the NH3+. So this is like ammonium ion, except one of the hydrogens has been swapped out for this weird thing, which is an ethyl group. So this is the conjugate acid of a weak base because it's an amine. So that's the best way to show that. Let's do it this way. This is a weak base, like ammonia. So think of this as a cousin of ammonia. This is a base, that makes this the acid. And because this is a weak base, this is in equilibrium, and so this solution will be acidic. You don't need to know the name of that or anything. What? That's a great question. So we're used to seeing NH3 plus H plus going to NH4 plus, right? That's what we're familiar with. And if you saw this, you'd take it this way. So this one is a little different because instead of this being NH4, one of those H's is this guy. This is subbing in for one of the H's. So here we've got ammonium ion. So what's going to happen here is we're going to take off one of those hydrogens and we're going to put this little monster. Okay? So it really is the same thing happening, but you are correct. The number, the subscript on that hydrogen looks wrong. You can also have an amine where you've got another hydrogen missing. You could have CH3 over here. And then this is going to have NH2+. It's this positive charge that tells us it's going to lose a hydrogen ion. instead of gaining a hydrogen ion. Because if it gained a hydrogen ion, then it would have a 2+ charge. Yes, I can. Okay, so this guy right here, this weird looking thing, right? It's got nitrogen and some hydrogens, and it's got a positive charge. And it's a little confusing because we're accustomed to seeing NH4+. This positive charge, though, tells me that this is going to lose a hydrogen ion instead of gaining a hydrogen ion. Because if this gained a hydrogen ion, which is kind of what we want to do so we can see NH4, then it would be +2. If we lose a hydrogen ion, then we get the neutral thing. And the reason the number on the hydrogen is off is because one of the hydrogens got replaced by this thing. So, okay, you got it now? Okay. Yeah, and the reason this is positively charged is it's from this guy right here, and we recognized chloride and took chloride off as an ion, so the rest of this has to have a +1 charge. So this is one of those things where until you take organic chemistry, you don't know what this thing is, but we don't actually have to know exactly what it is. We can still know how it behaves in acid-base situations. And we just kind of have to be okay with not knowing everything, which is a good life skill because it's how the rest of your life is going to be. Nobody knows everything. Okay, let's look at this one. KNO3. We had 2 ions, right? K+ and NO3-. So this can be written as the counter ion of a base. Is it a strong base? Yeah. This comes from KOH, a strong base, dissociates completely, and so this is neutral. What about NO3-? What acid is that related to? HNO3. Is that a strong acid? Yep. So this is also neutral. So then the solution is neutral. And then we got this guy down here. So we have Fe3+, and we have NO3-. And we look at that Fe3+, and we say that's confusing. Let's look at the NO3- first. So that comes from HNO3, which is, we just talked about, a strong acid. This is a strong acid, so then its conjugate base doesn't do anything. The stronger the acid, the weaker the base. So this one's going to be pH neutral. And then we got this guy. And I don't know about you, but I sometimes have a hard time remembering, is that going to act as an acid or as a base? I can remember the iron and aluminum ions do something, right? And you're correct, it acts as an acid. So cations, like this one and this one, can act as acids, and anions can act as bases. So this one had the potential for acting as a base because it's the conjugate base of an acid. And so this has to do the other thing. So this solution's acidic. And we can all just be thankful that they didn't give us an example where we had to compare Ka and Kb. Any questions? Mm-hmm.
It's with 6 water molecules, right?
Yes.
And then one of them breaks into H+ and OH.
Mm-hmm.
That's why you're getting acidic.
Yeah. I'm glad you can remember that.